Join us on a journey through one of physics' greatest transformations, where mathematical tricks became the keys to understanding reality. At the turn of the 20th century, physics faced a profound crisis. Light behaved in ways that defied all classical understanding. Let's begin by understanding the problem that troubled the greatest minds of the era. In the 1800s, physicists believed that light waves required a medium to propagate through, just as sound waves need air. They called this hypothetical medium the luminiferous ether. The ether was imagined as a rigid, all-pervasive substance filling the universe. Light waves would travel through it like ripples on a cosmic ocean. James Clerk Maxwell's electromagnetic theory predicted that light traveled at exactly 300,000 kilometers per second. But relative to what reference frame? Maxwell's equations gave this precise value for the speed of light, but they didn't specify whether this was relative to the ether or to the observer. This raised a critical question. If you're moving through the ether, shouldn't you measure a different speed of light? Just as you hear different sound frequencies when moving toward or away from a sound source. In 1887, two American physicists designed an ingenious experiment to detect Earth's motion through the ether. The Michelson-Morley interferometer split a light beam into two perpendicular paths, then recombined them to look for interference patterns caused by ether wind. The logic was simple. If Earth moves through the ether at 30 kilometers per second in its orbit, light traveling parallel to this motion should take longer than light traveling perpendicular to it. The expected time difference depends on the length L of the apparatus, Earth's velocity v, and the speed of light circa. For typical values, this should have been easily detectable. But the result was shocking. No matter how they oriented the apparatus, or when they performed the experiment, they found absolutely no difference. The interference pattern remained unchanged. The result was completely flat, a null result that contradicted all predictions of ether theory. This was one of the most important negative results in the history of science. Enter Hendrik Lorentz, a Dutch physicist who attempted to save the ether theory with a brilliant mathematical trick. In 1892, Lorentz proposed that objects physically contract in the direction of motion through the ether. This length contraction could exactly compensate for the expected time difference. The contracted length L prime equals the rest length L times the square root of 1 minus versus squared over c squared. This is the famous Lorentz contraction factor. A rod at rest has a certain length, but when it moves through the ether at high velocity, it physically contracts, becoming shorter in the direction of motion. But why would this happen? Lorentz suggested that the electromagnetic forces holding atoms together were affected by motion through the ether, causing a real physical compression. But length contraction alone wasn't enough. Lorentz realized he also needed to introduce a modified time coordinate, which he called local time. The transformed time t prime depends on both the original time t and the position x. The factor gamma is 1 over the square root of 1 minus versus squared over c squared. This gamma factor appears repeatedly in special relativity. At everyday speeds, it's essentially 1, but as velocity approaches light speed, it grows without bound. Crucially, for Lorentz, local time was not real time. It was merely a convenient mathematical variable that made the equations work. True time was absolute, flowing uniformly throughout the ether. By 1904, Lorentz and Henri Poincaré had developed a complete set of transformation equations. The position coordinate transforms as x prime equals gamma times x minus vt. The perpendicular coordinates remain unchanged, y prime equals y, and z prime equals z. And the time coordinate transforms as we saw before. T prime equals gamma times t minus vx over c squared. These transformations convert coordinates from a rest frame to a moving frame. Notice how the moving frame's space axis appears compressed. The remarkable property of these transformations is that they preserve the speed of light. If light travels at c in one frame, it travels at c in the transformed frame too. Mathematically, the quantity c squared, t squared minus x squared minus y squared minus z squared remains unchanged under Lorentz transformations. This is the key invariant of the theory. Let's work through a concrete example to see how dramatic these effects can be. Imagine a spaceship traveling at 0.87 times the speed of light. This is about 260,000 kilometers per second. With v equal to 0.87 c, let's calculate the gamma factor. Gamma equals 1 over the square root of 1 minus 0.87 squared, which is 1 over the square root of 0.24. This gives us gamma approximately equal to 2.04. This means time dilation and length contraction are doubled. Now here's the question. If 1 year passes for travelers on the spaceship, how much time passes on Earth? The answer is T Earth equals gamma times T ship, which is 2.04 times 1, giving us 2.04 years. More than twice as much time passes on Earth. In 1905, Albert Einstein published a paper that completely transformed the meaning of these equations. Einstein's revolutionary insight was that the ether was completely unnecessary. The constancy of light speed was not a coincidence to be explained, but a fundamental postulate of nature. Einstein boldly crossed out the ether entirely. There was no privileged reference frame, no absolute rest. The ether was a fiction. Einstein based his theory on just two simple postulates that overthrew centuries of physical intuition. First postulate: the laws of physics are identical in all inertial reference frames. There is no absolute state of rest or motion. Second postulate: the speed of light in vacuum is the same for all observers, regardless of their motion or the motion of the light source. Light travels at exactly c for every inertial observer, period. This seemingly simple statement has profound consequences. This raises a deep puzzle. How can light always travel at c, even if you're chasing it at 99% of light speed? The answer forces us to abandon absolute time. Einstein showed that if light speed is constant, space and time must be relative, not absolute. Imagine a light pulse bouncing vertically between two mirrors on a moving train. To someone on the train, the light travels straight up and down. But to someone standing on the ground watching the train pass, the light appears to travel diagonally, covering a longer distance. The distance traveled according to the ground observer is the hypotenuse, the square root of Vt quantity squared plus h squared, where h is the mirror separation. Since light must travel at c for both observers but covers different distances, it must take different amounts of time for each observer. Working through the geometry gives us exactly the time dilation formula. T ground equals gamma times T train. For Einstein, unlike Lorentz, these effects are not mathematical artifacts. They represent the actual structure of spacetime its. Einstein's theory revealed a deeper unity between space and time, merged into a single entity, spacetime. The fundamental invariant of spacetime is the interval delta s squared equal to c squared delta t squared minus delta x squared minus delta y squared minus delta z squared. While observers disagree about time intervals and space intervals individually, they all agree on this combined space-time interval. The light cone structure shows which events can causally influence each other. Only events within the light cone can be connected by signals traveling at or below light speed. Depending on the sign of the interval, we classify separations into three types. If delta s squared is positive, the interval is time-like. These events can be causally connected. If delta s squared equals 0, the interval is light-like or null. Events are connected by light rays. If delta s squared is negative, the interval is space-like. These events cannot causally influence each other. One of the most counterintuitive consequences is that simultaneity is relative. If two events occur at the same time in one reference frame, they will generally occur at different times in a moving frame. The time difference in the primed frame is gamma times delta t minus versus delta x over c squared. Even if delta t is 0, delta t prime need not be. Two events simultaneous in frame A, shown by the horizontal line, are not simultaneous in frame B, where the line of simultaneity is tilted. Consider lightning striking both ends of a train simultaneously in the ground frame. To passengers on the train, the strikes are not simultaneous. The time difference measured on the train is negative gamma times versus L over c squared, where L is the train length. This means there is no absolute present moment that extends throughout the universe. The concept of now is observer-dependent. Einstein's theory also revolutionized our understanding of energy and mass. The total energy of a particle is gamma mc squared, where m is the rest mass. At rest, when gamma equals 1, we get the famous equation, E0 equals mc squared. Mass and energy are equivalent. Let's calculate. How much energy is contained in 1 kilogram of matter? E equals 1 kilogram times 3 times 10 to the 8th meters per second squared, which gives 9 times 10 to the 16th joules. To put this in perspective, that's equivalent to 21 megatons of TNT, more than the largest nuclear weapon ever detonated. The momentum is also modified, P equals gamma m, versus, as velocity approaches c, momentum approaches infinity. Energy, momentum, and mass are related by this fundamental equation. E squared equals pc quantity squared plus mc squared quantity squared. Einstein's theory has been confirmed by countless experiments over more than a century. Muons are unstable particles created in the upper atmosphere by cosmic rays. They should decay before reaching the ground, but time dilation allows them to survive the journey. The muon lifetime in the lab frame is gamma times the rest lifetime of 2.2 microseconds. At high speeds, gamma can be 10 or more. In particle accelerators like the Large Hadron Collider, protons travel at 99.9999% of light speed, with gamma factors over 7,000. GPS satellites experience time dilation due to their velocity and due to weaker gravity. Without relativistic corrections, GPS would accumulate errors of kilometers per day. The net relativistic time difference for GPS satellites is about 38 microseconds per day, faster than clocks on Earth's surface. Beyond the mathematics, Einstein's work represented a profound philosophical shift. For Lorentz, the transformations were an ad hoc mathematical fix designed to save the ether theory from experimental contradiction. For Einstein, these same equations revealed the fundamental structure of spacetime its. What was a patch became a principle. The progression from problem to mathematical fix to fundamental theory shows how science advances through reinterpretation of existing mathematical structures. Einstein's genius was to ask, what if these transformations aren't just fixes, but are telling us something profound about nature? This marked a shift from mechanical explanations like the ether to principle-based physics, where symmetries and invariances guide our understanding. Special relativity became the foundation for all of modern physics. Quantum field theory successfully merges quantum mechanics with special relativity, describing particles as excitations of underlying fields. Einstein's general relativity extends special relativity to include gravity as the curvature of spacetime its. The Einstein field equations relate spacetime curvature, on the left, to energy and momentum, on the right. This is the foundation of general relativity. Virtually all successful physical theories of the 20th and 21st centuries are built on the foundation of Lorentz invariance. Modern tests of special relativity achieve precision better than 1 part in 10 to the 18th, yet no violations have been found. Let's clear up some widespread misunderstandings about relativity. A common misconception is that Einstein showed everything is relative. Actually, the opposite is true. The spacetime interval is absolute and invariant. It's only when we artificially separate space and time that we get relativity. Another misconception is that you can't exceed light speed because your mass becomes infinite. This is outdated language. The truth is that light speed is a fundamental speed limit built into the geometry of spacetime. Nothing with mass can reach it, regardless of how much energy you add. Some think time dilation is just a perceptual effect or illusion. Time dilation is completely real. The muon experiments and countless other tests prove this beyond doubt. One of the most famous thought experiments illustrates the reality of time dilation. Imagine identical twins. One stays on Earth while the other travels at high speed to a distant star and returns. Twin B travels out and back while Twin A remains stationary. Due to time dilation, Twin B ages less during the journey. The paradox asks, if motion is relative, why isn't Twin A younger from Twin B's perspective? The resolution is that the situation is not symmetric. Twin B must accelerate to turn around, breaking the symmetry between the twins. For Twin A on Earth, the elapsed time is twice gamma times the elapsed time for Twin B. If Twin B travels at 0.87 c for 10 years of their time, Twin A ages over 20 years. This effect has been directly measured using atomic clocks flown on airplanes. The traveling clocks consistently lag behind stationary clocks, exactly as relativity predicts. The story of Lorentz and Einstein teaches us profound lessons about science its. The same mathematical equations can have radically different physical interpretations. Mathematics alone doesn't determine meaning. Sometimes progress requires not new data, but a bold reinterpretation of existing data and theory. Einstein's theory was simpler than Lorentz's. It required no ether, no mechanical explanation. This simplicity suggested deeper truth. The unification of space and time into spacetime represents one of humanity's greatest intellectual achievements. The Michelson-Morley experiment's precision forced physicists to confront contradictions they might otherwise have ignored. Einstein's ideas initially faced skepticism. Even Lorentz never fully accepted that time dilation was real rather than apparent. Let's summarize this remarkable scientific journey. Hendrik Lorentz developed the mathematical transformations to save the ether theory from contradiction with the Michelson-Morley experiment. Albert Einstein reinterpreted the same mathematical equations as describing the fundamental structure of space-time itself, not just a mathematical convenience. Both Lorentz and Einstein were correct in their respective contexts. Yet Einstein's perspective has become the cornerstone of modern physics, revolutionizing our understanding of space, time, and gravity. The story of Lorentz and Einstein teaches us about the power of reinterpretation and the importance of simplicity in physics. Sometimes, what seems like a small change in perspective can lead to a profound revolution in our understanding of the universe.